science, but we like to learn from it so we can do more science. So this first balloon, it gave us a pop, louder than air. The second balloon gave us a fireball. Somebody tell me, and you all named it earlier, the gas that gave us the pop. Which one gave you? Oil? It's a good guess. Wasn't oil? Which one gave us the pop?
Explosion.
Somebody said it earlier. Helium. How many have ever seen a blimp up in the sky? Yeah. And they fill blimps now with helium. They used to fill them with the gas that gave us the fireball, which is hydrogen. Hydrogen. So you can see why they don't fill them with hydrogen anymore. Just one little match, that whole blimp would blow up. Okay? All right, let's do so. Which balloon would you like? Green, okay.
That's my favorite color.
Can
Can I go next, please?
What touch the side of that
Can I
balloon?
go next?
Dang, that one's too close.
Keep going. So, what's your first name?
Hers is bigger than yours.
This is Okay, so Greg, which balloon would you like? Red. You know what's interesting is nobody chose the red balloon, which is interesting to me. There's only one red balloon up here. Now, how many think this balloon is filled with helium with a pop? How many think it's filled with hydrogen with a fireball? How many think it's filled with whipped cream? Well, you guys are going to find out. All right.
Whipped cream. Why are you doing
Whipped cream explosion!
So what gas was that? Helium. Very good.
I wanted whipped cream.
You wanted that whipped cream one, huh? So you see that different gases, they behave differently. Some of them give us a pop, louder than air. They're combustible.
Bro, but it got
Some
hot
of them give
though.
us a fireball. They're flammable.
Dang, this smells like
All right, so the gas that we breathe in, that we like to breathe in, oxygen, is flammable. It's like hydrogen, it catches on fire. Also the gas that we breathe in, nitrogen, is combustible, like helium. So we have to have just the right amount of each one of those gases to be able to survive, to be able to breathe in. It's just the way that our planet's made, okay? So if we had too much nitrogen, and I went to light this lighter, it wouldn't light because it needs oxygen to burn. But if we had all oxygen, and that's all we breathe, and I lit that lighter, it would catch all the air on fire. So it has to be just the right amount of nitrogen, just the right amount of oxygen. We're the only planet that has that, okay? That's the way our planet's made. Okay, let's do another experiment. Let's see.
Can I be a volunteer? Can I be a volunteer? Don't ask me because he needs one. Oh.
So, you know, we were just looking at balloons popping all over the place.
Liquid nitrogen.
So this balloon is just filled with air, filled with ordinary air. And you know, if a 2-year-old were to ask you, hey, how does a balloon work? Well, it's pretty simple. We blow it up with air. How do we keep the air in there? Yeah, we tie a knot. But actually, there's a lot going on inside this balloon. All of the air inside this balloon is really a bunch of small little air pieces, or air molecules. And all those air pieces, or air molecules, are moving around very fast. They're bumping into each other. They're knocking each other into the wall of the balloon, and that's what keeps the balloon blown up. It's kind of like if this room were a balloon, and all of us were air molecules. And I don't want you to do this, but if I had everybody close their eyes real tight and jump up and run around as fast as you could in all different directions, well, you know what would happen. We'd be bumping into each other, knocking each other into the walls. So it would be kind of a mess. But what if I could make it very, very cold in this room? Somebody with a number, tell me a cold temperature with a number. -9. That is cold. How about a little colder?
Negative 30.
-30. That is cold. How about a little colder? -500. That's like crazy cold. How about if we could go like -300? What if I could make it -300? 300 below zero. In this room, if I could go 300 below zero, and I said, hey, let's all jump up and run around. Well, just like me, you would say, I want to sit here and stay warm. And that's what we're going to do to our air molecules in this balloon. We're not going to put any more air in, and we're not going to take any air out. All we're going to do is make it very, very cold. And to do that, we're going to use a gas that we're all breathing in right now. What are we breathing in? Oxygen, and we're breathing carbon dioxide out. What else are we breathing in? Begins with an N. Nitrogen. Yeah, very good. So if you take nitrogen and you super freeze it, it turns into liquid nitrogen. And so it is super cold. It's like 300 below zero. So that's why I'm wearing these very special gloves. So remember, we're not going to put any more air in. We're not going to take any air out. All we're going to do is make it very cold inside the balloon. Using a gas that's been super frozen to a liquid. So now, as we pour this nitrogen on here, our nice puffy balloon becomes,
How can you bring that much hair out?
Oh, and when you take
it
it out,
becomes
it's gonna
as
start
flat
blowing
as a
again.
pancake.
It's gonna
Wait a
start
minute.
blowing again.
Becomes as flat as a pancake. But now that it's out of the liquid nitrogen, it's warming up. And all of those air molecules are moving around faster and faster. They're bumping into each other. They're knocking each other into the wall of the balloon. They blow the balloon right back up. Is that cool? So now it sounds like an ordinary balloon. You want to see this again?
Yeah.
All right, so an ordinary balloon blown up with air. Remember, we're not putting any more air in, and we're not taking any air out. All we're doing is changing the temperature inside the balloon, okay? And when we do that, when we change the temperature inside the balloon, then all of a sudden the pressure of the balloon changes. And what this tells us is that temperature and pressure, they're kind of related. When one changes, the other changes. So as we change the temperature, we also change the pressure, okay? So now you'll notice, and it even sounds like a paper bag. Now, there it is, out of that liquid nitrogen, warming up. All of those air molecules moving around faster and faster. They're bumping into each other. They're knocking each other into the wall of the balloon, and they blow the balloon right back. Pretty cool. Now let me ask you this. Nitrogen, what does it want to be? Solid, a liquid, or a gas? What does it want to be? Solid, that's a good guess, not solid. A gas. It wants to, and we know that because we're all breathing in nitrogen, and none of us are breathing in a liquid. Otherwise, we'd be fish, right? So, we know it wants to be a gas. Now, you'll see when I pour this back in here, that's its last chance to be a gas. See how it's trying to be a gas? Well, once I pour that liquid nitrogen back in this big thermos bottle, and close this up, now it's trapped as a liquid nitrogen. And you know, pretty much everything has what's called a steady state, what it wants to be. So nitrogen wants to be a gas. What does water want to be? A liquid. What does a tree want to be?
Solid.
Solid. What does Jell-O want to be? Liquid and a solid. Yeah, sometimes it gets confusing, doesn't it? Because things go back and forth. It's like, oh, sometimes it wants to be a liquid, sometimes it wants to be a solid. Okay, very good. Those are called the states of matter. All right, what do you think? Should we do another experiment?
Yes.
All right. Let's do another one. I need a volunteer. I need somebody who hadn't been up yet. Okay. You haven't been up yet, have you? Come on up. Okay, come on up. All righty. Hey, how you doing? What's your first name?
He might be a mad scientist
Joshua.
too.
Got your glasses on? So Joshua,
Has yours reached your limit yet?
to hold this just like that, hold it way up in the air, and tell everybody what that is. A penny. Can somebody tell me what metal are pennies mostly made of? Copper. Very good. Just like this hollow copper pipe. Now what we're going to do in a moment is I'm going to ask Joshua, not yet, I'm going to ask him to drop that penny into this copper pipe that I'm going to hold over this bucket. And when he does, how many think that penny is going to land in the bucket? How many think it's going to hit the ceiling? How many don't know? And that's a good answer in science. That's why we do experiments. Let's find out. Joshua just dropped that right in the top. Okay, so that wasn't very exciting. Just landed right in the bucket. And we all know why, but only using one word. Can you tell me why that landed in the bucket?
Gravity.
Gravity. Very good. Okay, Joshua, hold on to this. Hold it way up in the air. Now he has this shiny steel silver ball. And we're going to do the same experiment. I'm going to hold the pipe over here. Wait a minute. He's going to drop it in the pipe over the bucket. And when he does, how many think that steel ball is going to land in the bucket? How many think it's going to hit the ceiling? How many don't know? How many want to find out? Scientists. Very good. All right, here we go. Drop that right in the top.
I knew it was good.
So let's do that again. There you go.
Wow.
Just drop that right in the top. So, only using one word. Can you tell me why this steel ball wanted to stay in the pipe? Only using one word.
It's magnet.
Magnet. Very good. This is a very powerful magnet. And magnets give off a force field. And that force field is pressing against the inside of the pipe and holding the magnet in there. So it stays in there, it stays in there, it stays in there. And then it comes out. Why does it come out?
Because gravity pushes it down, but it wants to stay inside.
Gravity. So we have two forces, gravity and magnetism. Okay. Now you know some metals, they are attracted to magnets, like paper clips. If I took this magnet and this bucket was full of paper clips, and I just dropped it in there with paper clips, all of those paper clips would attack this magnet. They would just, boom, stick right to it. But copper is not magnetic. Look, if we do it on the outside, it falls just like the penny. But if we do it on the inside, it stays and stays and stays, and then gravity pulls it out. Okay, now let me ask you this. This is a very strong magnet. But if I had a magnet that was twice as strong as this, how long would it stay in the pipe? You know exactly how long, actually.
Yes,
50, forever, infinity.
6
What?
seconds.
Twice as long, that's right. That's easy to remember. Twice as strong, twice as long. What if it were half as strong? How long would it stay in? Half as long. Very good. All right, let's hear it for Joshua. Good job, AMC. Put the glasses.
Can I go next?
All right, so let's do another experiment. So just like we were looking at forces, and forces working against each other, like magnetism and gravity, now we're going to look at forces that work together. How many have ever seen a chain like this? Yeah, it's a keychain. You use it for a keychain or a necklace or sometimes a bracelet or something. Different things to wear, different things on our keys or something. I got 50 feet of this chain, 50 feet. So this is really heavy. I mean, if I held this up over this table this high and I let it go, where would it go? Boom, it'd just land on the table, wouldn't it, because of gravity. But what I'm going to do, though, is something a little different. I'm just going to I'm going to hold it up high like this. I'm just going to pull on that chain and let go, and we'll see what happens. Now, the chain's going to fall here, but this is not where the action is. Where you want to watch is right up here.
Okay.
Okay, here we go. So what I need is a 5, 4, 3, 2, 1 count.
5,
Tell me, what did you see?
He wasn't even hitting.
What did you see?
I was hitting on the ball.
I saw that the chain was going up.
Very good. It didn't just fall, it jumped up out of there, didn't it?
Commercial break,
so
all
heavy.
singing must be legal.
So we had two forces working. We know gravity, that's why it fell on the table. But then we had this force called momentum. That's why it jumped out and came very fast. Here's what momentum is. If I'm on a bicycle and I'm at the top of a hill and I take my feet off the pedals and I don't put my feet on the ground, I'm just holding on, what's gonna happen to that bike? It's gonna go down the hill. Is it gonna go slow or fast? Speedy. It's gonna go faster and faster and faster, isn't it? That's momentum. And that's what happened here. Once we pulled that chain, once it started out, it went faster and faster and faster and pulled the whole chain out. Two different forces, yeah. Oh, actually it takes me about 10 minutes to unwind this chain and get it all back in order. So we'll move on to our next experiment. I like that one, don't you? So that's 50 feet of chain. Just think about if I had 150 feet of chain and I stood on top of a tall building and pulled the chain and it went all the way down, it would jump even further because it gets a little more momentum, okay? It's kind of like if I'm on a hill that's this high, I get some momentum, but I don't go real fast before I level out. But if I'm on a hill that's way high, you get faster and faster. That's how momentum works. All right. So let's do another experiment.
Are we going to do the elephant too?
I need a volunteer. Now I need a very brave volunteer.
I'm a brave one.
This is tough.
She doesn't look brave. She doesn't.
Hi, how are you?
You can't judge people like that.
Yeah, I know.
Cause she may save your life one day.
What I have here is water. You can touch that. No hurt you. Is that hot or cold? Warm. Kind of middle, kind of room temperature. Yeah. So I've got some water. Now in the summertime, which is right here now, when it's really hot, how many people like to go swimming?
Not mad.
Yeah, and so does Brooklyn, which is great. So let's see, I've got water. Brooklyn likes to go swimming. How many of you would like me to take this water?
Yeah.
and dump this on Brooklyn's head? I mean, we couldn't do that, our clothes would be drenched all day, but hey, there might be a way we can do this. Here you go, Brooklyn.
She's
Take
gonna
this
do it
towel
for real?
No.
and wrap around the back of your shoulders like a shawl.
Could I
And
go?
pull it in real close around the neck. Perfect. I mean, hey, now her clothes will be dry. I mean, her hair's gonna be drenched, water dripping off her chin, but at least her clothes will be dry. So do we still wanna do this? It wouldn't be a science show if we didn't mix chemicals. And of course, water's a chemical, probably the one we're most familiar with. And then I have here a little bit of a powder. And I'm gonna take this powder, dump it into this water, hold this over Brooklyn's head and count to 5, and then Brooklyn's going swimming. All right, you wanna pull that towel in real close. All right, so
It's gonna be frozen.
let's see now. Here is the water. Here's the powder. 1, 2, 3, 4, 5. You can look up.
It froze.
Oh, look at that. You can touch that, it won't hurt you. It's weird. Yeah, it's weird, isn't it? Why don't you leave me the towel? You keep the glasses. Let's hear it for Brooklyn. Good job. Okay, so we started with water, a liquid, and now we've made this solid. And this is something that all of you have used, and this is being used in most of your homes right now.
Ice.
What is it? Ice. That's a great guess. It's not ice.
Frozen water.
Frozen water like ice. It's not that.
Ice water.
Yes. You stretch it. Okay. Yes.
I think it's the diaper powder that's in the diapers.
You think this is a
Diaper powder.
Yeah.
You are exactly right. This is how they make disposable baby diapers. So Brooklyn can say she came today just to put her hand in a baby diaper. Okay? And the reason is that little bit of powder absorbs or locks up 100 times its weight in liquid. It's called superabsorbent. Now, we can take this chemical reaction and we can make it go backwards. Just by adding ordinary table salt. Just like out of a salt shaker, which is sodium chloride. So when we add this sodium chloride, which is salt, just like the salt you would put on something like Parmesan or something, and we mix it all up, then our solid goes right back to a liquid. So now, we're right back to a liquid. Now, how many think we should have Brooklyn come up and dump this on her?
Me.
No, we won't do that. Actually, I'll walk over to her and dump it on her head. No, we won't do that. So what does this mean? You know, we like to do cool science, but remember, we like for it to mean something so we can do more science. So what this means is, if you lived in Florida down by the ocean, and tomorrow you went to the beach, it'd be a great day, and you're there at the beach and your little baby brother or sister is in their diaper and they're sitting on the beach, and that salt water from the ocean comes up and hits their diaper, that diaper's just gonna fall apart. But yeah, but we live in Indiana, so we made the swimming pools. So you get a chance to go to the pool this summer, and your little baby brother or sister is over at the kiddie pool, and they're in their diaper, and they're sitting there in their diaper. Well, unless they have a very special type of diaper, that diaper's gonna get bigger and bigger and bigger, because it's trying to absorb all the water in the pool. It's called superabsorbent. Superabsorbent. All right, very good.
Diaper's gonna be tough.
What do you think? Another experiment?
Yes.
All right, so what I need to know is, how many future scientists do we have here today?
Bill the science guy.
Oh, very good. Well, I think Bill Nye the Science Guy is already a scientist. Which he is. Okay, so, can somebody tell me, because we've got a lot of people that are interested in science here, can somebody tell me what is the most common chemical that we use every single day? What is it?
Soap.
Soap, that's a good guess. We use soap every day, which is good. There's something even more common. Water, yeah, water. I mean, we use water all the time. Wash our hands, take a shower, drink, all kinds of stuff. And of course, water is blue liquid, right?
Yeah.
It's a blue liquid?
No, so it's a little
Orange liquid.
It's a little bluey and a little white.
Clear,
clear.
yeah. So most of the time when we see water, it's clear, okay?
How is this yellow?
This has got a little yellow because this is not water, this is hydrogen peroxide.
Oh, cool.
And hydrogen peroxide looks a lot like water, but it's a lot different. Actually, we use hydrogen peroxide in our homes a lot of times for cuts. If you get a cut on your hand or on your finger, you put hydrogen peroxide on it, it kills the germs in that cut. So if hydrogen peroxide is used for cuts, and you put it on your hands, why in the world am I wearing these very special gloves to protect my hands?
Because you didn't have any cuts.
I don't have any cuts, but there's another reason.
Is it very strong?
Very good. This is very strong. In fact, this is 10 times stronger than what you would put on a cut. So if I took this glove off and I poured this on my hand with no glove, it would feel just like I went over and put my hand right in a fire. It would burn that badly. So this is a pretty dangerous chemical. And you know, it wouldn't be safe to pour it down the drain. And it wouldn't be safe to leave it sitting around the school. So I think what we want to do, let's take that liquid and let's just tear it in half. Just like you would take a paper towel and tear it in half, let's just tear that liquid in half. Yeah, so you might think, how can you tear a liquid in half?
You Fred?
Well, to help us see this, let's add a little bit of dishwashing soap.
It's gonna turn into.
And let's mix that all up. And let's add a little bit of food coloring.
Please be.
It's gonna be frozen.
We'll add a little bit of food coloring. So now we have a red, soapy hydrogen peroxide solution. Now remember, what we want to do is we want to tear this liquid in half. And when you tear chemicals apart, or when they fall apart on their own, It's called decomposition, decomposition. This would fall apart on its own if we let it sit here for 90 days.
90 days?
Yeah, we don't want to wait 90 days. And you know, in our labs, we don't want to wait 90 days for this reaction, and 2 weeks for that experiment, and a year for that experiment. So we use chemistry to make our chemical reactions go faster. And that's what we're going to do here. We're going to use a type of chemical known as a catalyst. A catalyst. This is sodium iodide, and all a catalyst does is take a chemical reaction and make it go very, very fast. When I add this catalyst to this hydrogen peroxide, this 90-day reaction is going to happen in 2 seconds. 1, 2. Let's see how it works. All right. Give me a 5, 4, 3, 2, 1 count.
5, 4,
3, 2, 1.
Whoa.
This just looks like what Mr. Chunderman did.
Ew.
Oh, that's like food.
Cool.
That's like a food actually.
So,
That is more than that's in there.
yeah,
A lot more.
more than what we started with, isn't it? That's a good observation. We filled it up
It's
even
still
more.
coming out.
Yeah.
May eat it?
There's a lot more to go.
So, somebody tell me, what did you see? What did you see? Anybody?
I just saw that.
This just looks like what Mr. Chunderman did. When he
Yeah, it came out very fast, didn't it? If I had taken this, what's this stuff called?
baby diapers.
Begins with a C. Begins with a C, a catalyst. Let me hear everybody say catalyst. Catalyst. If I had taken this catalyst and dumped it in here and pressed down very, very hard, this would have built up pressure, and it would have exploded. Okay?
No,
Now, let me ask you this. How many think this is hot?
Nope,
How many think it's cold?
it's warm.
How many think it's room temperature? Okay, it's actually, all three are good guesses. It's actually very, very hot. Right, hot. And the reason is, when you tear chemicals apart, they don't like that. So they give off energy, many times in the form of heat. It's no longer hydrogen peroxide. We tore that apart. It's now just water and food coloring and soap. But the water in there is so hot, it's actually boiling. It's boiling hot. So we like to give our experiments very scientific names so we can talk about them. So we call this experiment elephant toothpaste. Elephant, you knew that, didn't you? Elephant toothpaste. Very good. Elephant toothpaste. All right.
No, it's for elephants.
So let's do another experiment.
I got my new J's out the box. Hold
I
on.
need a volunteer.
This time a brave one.
Well, pretty much a brave one, yeah. Let me move a few things around here so we've got some space to work. Good volunteers. All right, here. Hey, how you doing? What's your first name? Harrison. Okay, all right. Put your glasses on. Let me grab a couple things that we need here, Harrison.
Thank you.
Stand right here. Okay, so what we're gonna do today is, you know, it's been getting kind of warm out. We're with Harrison's help, we're gonna make some snow. We're gonna make some snow.
Gonna make it snow.
And so I'll show you our snow.
Favorite part.
So here's our snow right here.
Snowball.
So there we go. We've got our snow.
That's snow.
Doesn't quite look like snow, does it?
It looks like salt.
That looks like
Yeah.
salt.
It looks like salt, doesn't it?
looks like
Actually, you
powder.
can feel that, Harrison. It won't hurt you. Feels like salt, doesn't it?
It feels like
Yeah.
powder. It looks like powder.
Yeah, it's sugar, or maybe sugar even. So you think, what's the deal? I thought we were gonna make some snow. You know what? What's the main ingredient in snow? Water. So, just so happens I've got a bunch of water. It's ordinary water. And what I want you to do, Harrison, is I want you to take this gallon of water and I want you just to pour it. I'll hold the bucket. You just pour it in there and kind of pour it in a circle, getting all of that powder wet. And you're gonna pour all of this in the bucket, okay? All of that. I'll hold the bucket for you. So just, yeah, very good. That's perfect. Just keep doing that. Keep pouring all around to get it all wet. There's some down there. I'll try it for you. Very good. Keep going.
Because the water
Keep
inside of
going.
it. The water is going inside of each
Yeah, you're
one.
doing great. Excellent. Put that all in there. Very good.
That looks like.
Okay, so now we got that whole gallon of water in. Now we're gonna do the fun part. So you might want to, is it okay if you take your jacket off for a second and just set it over there? Because you don't want your jacket to get into this. Very good. Now I want you to take your hands, and I want you to go all the way to the bottom and mix that all up. It won't hurt you. Mix it all up. Good, good, good. Now, as you're mixing that, let me ask you, is that hot or is it cold? Cold. And it's going to get colder and colder and colder. Because this is how they make artificial snow. You know, if they want to have snow in the winter, but it's not cold enough, they don't have enough snow, what they'll do is they'll use this powder and water. Just keep mixing it up. They use this powder and water, mix them together and blow them out with a big fan over some hills. And all of a sudden you got hills that you can sled on and slide on and all kinds of things. Now let me ask you this, Harrison. Is this snow, is it real hard and jagged like if you fall on the rocks? Or is it soft? Yeah, it's fuzzy soft. In fact, if you fell on this snow, it wouldn't hurt a bit, would it? All right, very good.
I'll look
so
at-
kind of
I'll see
lift
his
your hands
face.
out, tap them together. Now, who's this guy sitting next to you? Darren? Okay, so what we're gonna do is we're gonna have Harrison, your hands got stuff all over him. You're gonna go over and just wipe your hands on his shirt, okay? No, just kidding. Just kidding. I got towels for you. Okay, there you go. Let's hear it for Harrison. Good job. Now, we started with that little bit of powder and a gallon of water.
Give us a little.
Now, a gallon of water is 4 liters. You see, these are all marked off here. 4 liters is right here. You see, it's kind of growing. It's up to 6 liters. And the more it sits, it'll grow about up to maybe 7 liters. So you think, wow, this just grows and grows, doesn't it? Because that powder, excuse me, super absorbs a bunch of